Okay, welcome again to our journey into number theory, and this is going to be the final section for chapter 4. And I want to just finish here by looking at actually explicitly evaluating, giving some nice formulae for the evaluation of L of 1 and chi, where chi is a non-principal character modulo k. And we're going to construct a nice integral formula for this one, and we'll then do some calculations on actually explicitly finding some values of this. So we start off with, we've got L of 1 and chi, and we want chi not principal. So chi is a non-principal character modulo k, and n is a positive integer. Now I'm going to go back and look at this sum again of chi n over n, where little n goes from 1 up to some multiple of capital N. And what we're going to do is we're going to write the 1 over n, I'm going to write as an integral. So I'm going to write 1 over n as just the integral from 0 to 1 of t to the n minus 1 dt, and then the sum is independent of t, so that just pops in there. Now I'm going to start writing out the terms of this, and we're then going to use the fact that the characters are periodic to pull things together a bit. So this is the integral then from 0 to 1 of, so I just start writing out the terms. So it's chi of 1 times 1, chi of 2 times 2, chi of 3 times t squared, and so on up to chi. I go up to chi of k, t to the k minus 1. Now once I go to the next number up, then chi of k plus 1 is just going to be chi of 1 again, because it's periodic of period k. But now the multiplier here is t to the k, and I do the same thing all the way up to here. And then once I get to here, chi of k plus 1 is back to chi of 1, and so I can do this all the way down to here, and I end up with this sum. Now you can do that, of course, by the periodicity of the chi. So you can now take a chi 1 as a common factor out of all of these terms, and then a chi 2 out of all of these terms, and so on. So I rearrange, these are all finite sums, of course, so I can just rearrange them in this way, and then chi 2 times that, and so on down to chi t to the chi k to t to the k minus 1 times that. Then of course, and I'm then going to integrate all this from 0 to 1 dt. Well, of course, I can then, of course, take this out as a common factor, and so I end up with just the sum now, the integral from 0 to 1 n equals 1 to k, chi n t to the n minus 1, times this sum in the brackets here. And this, of course, is a nice geometric series, so I sum that one. And then I'm going to split this up now into 2 bits. So I'm going to write this, I'm going to take the terms with the chi of n t to the n minus 1 over this. I'm going to call that lambda of t 1 minus t to the k, minus lambda t to the capital N k on 1 minus t to the k, where this lambda of t is just this sum. Now I want to examine what happens to this sum, as this sum, of course, I want to see what's happening to this sum as t goes to 1. So by the way, notice as t goes to 1 here, this is going to 0. Yep, so this is going to 0, so as t goes to 1 it's going to 0, so both of these integrands here are becoming improper at t equals 1, but we're getting 0 over 0. So that means I can then try and use L'Hopital's rule to see if these expressions have a limit. In particular, I'm going to look at this one here. As t goes to 1, this is going to 0, that's going to 0, so I can use L'Hopital's rule. So I'm going to differentiate lambda t with respect to t, which, given the expression for lambda, gives me this. Bring the power down the front, decrease by 1, and differentiate the bottom with respect to t gives me this. I can do a little bit of cancellation of the powers of t. So as t goes to 1, these terms disappear, and I can take the minus 1 on k out, and so I just get this sum, which is a finite sum. And I'll give that, and now I can split this up into the sum of n times chi of n, and then minus the sum n equals 1 to k of chi of n, but we know that that's 0. And so this just collapses down to this one, and I'm going to, this is just a constant, so I'm going to call it capital C. So that means this integral that we've started with, the first term of this converges, even though it's technically an improper integral, it's a naught over naught, but it converges. Now for the other term that we got was this one, and I want to get a bit of a bound on this one, so this is less or equal to the absolute value in here, and this one here, remember we've seen, is less or equal to c, and so this is the absolute value of this c that we had before times t to the nk. I can integrate this one, which gives me this from 0 to 1, and now as n goes to infinity, this is a constant, so this is just going to 0. So as n goes to infinity, that second term in that sum goes to 0, and so the L of 1 and chi now, of course, is the sum to infinity of this, which simply means we're letting capital N go to infinity, and as capital N goes to infinity, from that earlier work that we did, the second integral is going to naught, and the first one was independent of n, so that just copies there. And I can now substitute in, this one is just the sum of this one, that's how we started things off, times 1 on t to the k dt. So this gives me an integral formula now for L of 1 and chi. So let me just do a couple of examples here of this, applying this integral formula. So for example, if we look at chi 3, the non-principal character modulo 3, if there's only one of them, then the character values are 1 and minus 1. So we get 1 minus t on 1 minus t cubed. And this is a really easy integral to do. You can factor the bottom, and then you get 1 on 1 plus t squared. You can complete the square and so on. And you get this one as the value of L of 1 and chi 3. Interesting that this L function of 1 and chi 3 has got some pi's in it. It's rather nice. If we take if chi is the real non-principal Dirichlet character mod 5, remember there's the principal character, there's one non-principal real character, and the other two have got complex numbers in them. So again, you do the same thing. The character values are 1, minus 1, minus 1, 1, if you look back to earlier character tables that we did. And so I get this integral here. This is a little bit more complicated. Notice again, you're getting 0 over 0 when x is 1. So you can factor out 1 minus x out of the top, factor 1 minus x out of the bottom and cancel them, and you get this expression. Slightly more difficult integral, but symmetry tells you here to put y as x plus 1 on x. And having done that, and a little bit of algebra, then you end up with this integral, which is a much easier one, and this leads to a logarithm with some root 5s in it. So that also is interesting. The L function here, the non-principal L function at 1, leads you to this expression with some logarithms in it. Well, I leave you to show that if you do the non-principal real characters for chi of 4, chi of 6, then you can show that the L functions, the one for chi 4 gives you pi on 4, and L of 1 and chi 6 is pi on root 2 root 3. Now, I just finished by commenting that there's a very surprising relationship, connection, which takes you into, well, algebraic number theory, connections between the evaluations of these L functions and the fundamental units in the rings Z root K. So let me just finish with a little example of this. So we have shown above this fact. We just saw that the L of 1 and chi5 was 2 on root 5 log 1 plus root 5 on 2. And I just tantalised you by telling you that the fundamental unit in Z root 5 is epsilon is 1 plus root 5 on 2, and these are connected. So the L function is giving you something times the logarithm of this fundamental unit in this ring Z root 5. Now the fundamental unit simply means that every unit in this ring, every invertible element in this ring, every element where you can write 1 over it, is given by some power of the fundamental unit. That's what we mean by the fundamental unit. So there is a nice connection between these L functions and the algebraic number theory, these fundamental units in these rings. And I leave you to investigate that further and to learn more about the connections there, but that's as far as we will go in that direction. In the next chapter we're going to start looking more carefully at the Riemann zeta function.